All right, we're going to continue our study with electricity, and we're going to be starting our circuits today. So first, we need to cover some new vocabulary, some new verbiage that we can all communicate well in. First, we have voltage. This is our electric potential. In other words, the difference in charges. And what I'm talking about is the difference in the sides of the electric source. So we might have something like a battery here that has a positive and negative side. And so the difference between these charges would be our voltage. The variable for voltage is capital V. The units, it's measured in volts. Also a capital V. Now, when we get into circuits, we're going to be doing some circuit diagrams. The symbol for voltage, okay, so we'll be doing the variable, units, and the symbol for all of these is this. You have a long line and a short line. That's a little over exaggerated. The long line is positive, and the short line is negative. I remember that because if we think of these as, oops, I didn't put the negative sign there. If we think of these as sticks, we put the two sticks of the plus sign together, we get a long line. We only have one stick for the negative sign, so it just gets a little short line. Now, you know some voltage sources already. Batteries like this, that looks like our AAAs. You have your AAs, your Cs and your Ds. All of those have a voltage of 1.5. Not too big. Of course, you also have the rectangular batteries. Those are called 9 volts. And a 9-volt battery, as you can guess, has 9 volts. The little circular disc batteries that you have in your watches, some calculators, those are all about 3 volts. And if anybody's ever worked on a car battery produces about 12 volts. When it's running, the alternator is producing about 13, 14 volts, and that's to charge the battery. So you have that. Another common source is, of course, just your common wall socket. It's slightly different than the batteries. That's why I put it over here. The voltage coming out of that is 120 volts, so on average. So let's be careful with those. So there's your voltage. Next idea is current, and current is the measure of the flow of electrons. Now, the flow of electrons is interesting. The effect when you turn on a circuit is that it's almost instantaneous, right? Almost the speed of light. Well, that's not the electrons traveling at the speed of light. That's the flow of the electrons, or the effect of them. So if one electron moves just a little bit, that pushes the next electron fast, and the next electron, and that process happens near the speed of light. And so you get all these electrons in a line moving, and as soon as one of them moves, they all move. And that's how things happen so quickly when we turn on electrons. It's not like we have to fill up the circuit with electrons already there. We just have to get them moving so that we have a current. Once we get them moving, we have a current. Let's see, the variable for current is capital I. I don't know why. It is technically, for those that are in calculus or going that way, that is the change in charge over the change in time. So how much charge, how many electrons are passing a certain point in a certain amount of time. And then units, it's measured in amperes. Abbreviate that actually with amp a lot. You can just use capital A, Either one of those is fine. But let's talk about current. Now, you don't really have a symbol for current. You just have a complete circuit. So here's our voltage source. We would put wires on there, which is just straight lines. Once we complete that, then a current's going to flow. Now, we would draw this current like this, going from positive to negative. This is called conventional current. When they started drawing current diagrams, they thought that electricity went from positive to negative. Once we discovered the electron and the other subatomic particles, we realized that it was the electrons that are flowing, and so it should flow from negative to positive. But like the fundamental theorems of thermodynamics, where we introduced the zeroth law because the first couple of laws were already widespread, this was already out there, very widespread, and we did not want to change it and cause confusion on which diagrams are which. And so we call this conventional current, knowing that our circuit diagrams are going to work, even though the original idea was backwards. The way they're designed, it all still works. So that leaves us with resistance. Resistance is, or something that has resistance, slows the flow of the current. Typically, to use the current. So we're going to simplify things way down, and we're going to say that anything that's using current or is just a resistor. We did just use plain resistors, as we saw in that circuit before school got out. But anything that slows down the current or uses current, we're going to use this symbol for a resistor. The variable for resistor is R. The unit is ohms. And we're going to use the Greek letter omega for the units. Okay, so we have volts, current, and resistance. All of these, voltage, current, and resistance, are related by Ohm's law. Yep, here's another law, so you need to pay attention to this one. And Ohm's law just basically says that the voltage equals I, which is current, times the resistance, R. So in the most basic circuit that you can have is this. We have a voltage source. We have some kind of resistor, something that's using the electricity, and our current I going around. Okay, if we don't have a resistor, then we have what's called a short circuit, and it's just draining the voltage source, which is very dangerous. It just creates heat, and just keeps going and going until you drain the battery or until you burn out the wires. If we look at this first example here, to use this Ohm's law real quickly, a typical space heater has a resistance of 11 ohms. When plugged into a wall socket, the heater is exposed to the equivalent of 120 volt potential difference. That's that wall socket that we talked about. Draw a circuit for the heater. You're not going to have to do this often, and we're just going to do it in class. Determine the current and draw the direction of the current flow. So let's go ahead and draw our circuit. It's like this, with our heater over here. 120 volts, you typically write your voltage here. So knowing that this is 120 volts, we know this is a wall socket, so we're plugging this into the wall. Our current's going to flow like this. That was the third thing they asked us to do. And here is our heater over here. So this is like the wires, the plug, and the actual thing is over here. We are given our resistance, 11 ohms. We're given our voltage of 120 because it's plugged into the wall. So we use Ohm's law. Solving for current, we divide both sides by R. We get V over R. I equals 120 divided by 11, leaving us with 11 amps. So we have 11 amps coming from this heater. And Ohm's law is very simple. Two things multiplied together gives you V. Y'all can handle that. I'm not too worried about that. I do want to introduce electric power here before we end. Electric power is just the current times the voltage. Using Ohm's law, we can, for example, we can substitute V, we can substitute IR in for that, and we can get that power equals I squared R. Or solving some other way, we can get power equals V squared over R. So we can use any one of these for power, just depending on which one we have to begin with. And don't forget that power is measured in watts. So let's look here. A typical space heater. So back to our space heater. Uses 120 volts wall socket, draws 11 amps. How much power does it use? So power, we're just going to use this. We have voltage, and we've got amps. That's I. So we're just going to use the very first one here and do 11 times 120. So that comes out to, with two significant digits, 1300 watts. Okay, that's a lot of power. Space heaters are dangerous. You have to be careful with them. They can overheat and draw an excessive amount of electricity. So be very careful with the heaters like that. This next motor, it draws 1.19 amps of current. So we're much smaller. The heater was 11. This is less than 2. And has a resistance of 101 ohms. Assuming the motor is 90% efficient, what is the power output? 90% efficient, remember our thermodynamics. No motor, no engine is 100% efficient. So we're going to lose some energy to heat, sound, and stuff like that. So we want to do power. Let's see what we have here. We have I is 119. We have resistance of 101. So if we look back up here, I and R, that's this one. We can use I squared R. Now we can use I equals, or P equals IV, but we would just need to calculate V using Ohm's law. But this is much easier. So P equals 1.19 squared. R is 101. Multiply that together with 1, 2, 3 significant digits. We have 143 watts. Now that's at 100% efficiency, which we don't have. 90% of 143. So remember 90%, so we write that as a decimal, so 0.9 times 143. Now we're going to consider this exact, so it doesn't change our significant digits, and we get 129 watts.